the hydration of carbonyl groups go very much along the lines of what one might expect this reaction to go like. It can be done via acid or base. They're both very simple. We'll look at the acid first. Carbonyl groups are polar. This is partially negative, this end is partially positive. Adding acid to this will protonate the partially negative end, like so. We'll add a hydrogen to the carbonyl group, whatever it happens to be, ketone, aldehyde, something else. And this will allow water to more easily act like a nucleophile on it. So we'll come in and attack this is the partially positive end. It will react as a nucleophile. This set of electrons will go up to the oxygen and create this. So we've got basically an alcohol with an extra proton. Another water comes along and removes that, and the result is a diol, two alcohol groups. Now looking at the base catalyzed, it's very similar. It just, instead of adding the proton first, it adds a hydroxide. This will react as a nucleophile, again partially positive this end. This is partially negative. And obviously this has a negative charge. We'll add to the backside here. Very similar. Instead of having a positive charge, there's a negative charge here, and it will take a proton from water and create the diol as well. So both very simple mechanisms, they give the same thing. The only other important thing to note about these kinds of reactions is that these carbonyl groups are constantly in equilibrium. And so the amount of product that we'll get is going to depend on how stable this carbonyl group is. So the important trend to remember is that the more stable the carbonyl group, things that can donate electron density, they favor the carbonyl. So ketone having two methyl groups is the most stable out of the ketone, aldehyde, and formaldehyde. If we look at the equilibrium constant, the hydrate over the ketone and water, the equilibrium constant for the ketone is 0.0002 compared to an aldehyde, which is 0.7. So there are many orders of magnitude of difference between this equilibrium constant and this equilibrium constant. And of course, comparing to formaldehyde, the equilibrium constant is 40. So it's much more favorable to the hydrate. And then of course there are other things that we can do to make it even more favorable to the hydrate. For example, a common one is something like this. So these chlorines are all electron withdrawing. So normally with the ketone and the aldehyde, these were slightly more stable than formaldehyde. Well, this one much more stable than ketone, because these have electron donating effects. This is very negative, so it's going to pull a lot of the electron density from this carbon, but these methyl groups will be able to donate electron density like so, stabilizing it. Since there is only one methyl group here, it's not as stable as this one. So it's going to favor the hydrate more than in the example of the ketone. But here, this group has the opposite effect, since these are all three electron withdrawing. It's actually going to destabilize this, because this will actually not donate anything over to here. It's actually probably going to withdraw even more. So this is very unstable, so this will highly favor, I can't remember what the number for this was, I think the K was like 500 or so, so it's much more favorable to the hydrate than to remaining in the carbonyl group.